Hello, hello. Let me know when you can see and hear me, please. Hi. Who do we have? Hello. Hi, Chinwendu. Hi, Chinwendu. Oh, hang on. Sorry, I'm hearing myself echoing. All right, let's stop there. Hi, A. Hi, Aria. Hi, Jawahir. Hi, Jade. Hi, Bella. Lovely. Do we have anyone else? Anyone that's over on TikTok? Hopefully you can see and hear me over there as well. But don't forget that you can only message on YouTube. So if you want me to see your questions, then make sure that you come over here. That is unlikely for today, but I can add that into a future live that we look at some organic analytical techniques. Okay, so I'll actually, do you know what? I'll make a note of it now, just so that I've got a list of some of the key topics that we really want to focus on. Okay, but today's focus is on shapes of molecules. Hi, Victor. So we're going to get started, right? So Born Harbor cycles. Again, there's a list, Miss Burb. There's a list growing, but I will definitely add that on. Okay. Okay, oh my gosh, Aria, I am very jealous. I'm actually really jealous. Okay, Jawahir, I am well. How are you? Okay, let's get started. So, shapes of molecules and ions. And as I was saying to my year 13s earlier, this is actually the launch of a new strategy, okay, a new strategy for determining the shape of a molecule or an ion that even works for oxygen. So for my year 12s, the method that I taught you in lesson is great, is wonderful, but we know for oxygen it doesn't work quite as well. This method works every single time. So stick with me. Okay. So let's start by making sure we understand the basic shape. So how redox is coming up very, very soon in the next couple of weeks. So our basic shapes are based around how many pairs of electrons we have around our central atom. So if we have two pairs of electrons or two regions of electrons around our central atom, then our shape is called linear. And our example is carbon dioxide, okay, where our bond angle, of course, must be 180 degrees. Okay, we will absolutely be looking at lone pairs as well. Yeah. We're going to do like a crash course on all the shapes. So for the public live streams, Jawahir, there's no workbook. That's special, right, for our MES courses. So for this, following along and asking any questions as they come about. Feel free to make any notes as you are as well. Okay. So if we've got three electron pairs, we've got trigonal planar. Our common example is BF3. That's one that we really should just recognize, where because we want those electron pairs as far away from each other as possible, what bond angle must we have here, or bond angles rather? Bond angles, bond angles. Thank you, Chinwendu, 120 degrees. Okay, and then four, this is where it gets a little bit more interesting because we're no longer just flat, so planar. Instead, we are tetrahedral, which is in three dimensions, right? So we will have one bond going up, one coming down slightly further than 90 degrees. Then our solid wedge means that it's coming towards you, so out of the board towards you. My wedges are always a little bit dodgy, but I hope you can forgive me. And then a dashed wedge, which shows that it's going behind you. And bond angles for tetrahedral. Ooh, lovely. XEF, you mean XEF4? Absolutely, Aria. Lovely, 109.5. Well done, well done. And all of these bond angles are the same, 109.5 degrees. Okay, lovely. Let's go to our final two main shapes. So the basic shapes that all other ones are based off of. So we've done 3, 2, 3, 4, and then we'll go to 5. For 5 electron pairs, that's trigonal bipyramidal, where we have a central atom, then we have one bond going up, one going down, and then we have the final three bonds around the equator. So like a triangle, one coming out to the side, one coming towards you as a solid wedge, and then one going back as a dashed wedge. Here we've got two different bond angles. What are they? What are they? What are they? Ooh. Lovely, Saha. Wonderful. We've got 90 degrees between our axial and equatorial, and then we have 120 degrees between the three around the middle. So two different bond angles for trigonal bipyramidal. Tasbiha, what do you mean by the rules? What do you mean by the rules? How many rules are there? Then for 6 electron pairs, 120 because it's a triangle around the middle. So just like our trigonal planar, they were 120 degrees away from each other. Around the middle, that's still a triangle. It's just flat like that. So still 120 degrees each. Okay, it doesn't look quite like 120 degrees. That's because, oh gosh, how do I do this? One is coming towards you like that, and then the other one, oh gosh, can you see my, no, you can't see my arms. Okay. Tasbiha, the idea of VSEPR is that we want our electron pairs to get as far away from each other as possible. That's the baseline. Okay, and then we're going to build on that in a moment. Finally, 6 electron pairs, octahedral. So kind of similar to our trigonal bipyramidal, but this time we've still got one up, one down, but instead of 3 around the middle, we're going to have 4 around the middle. Oopsie daisy. Again, my dodgy wedges, they'll always be dodgy, and I think I'm okay with that. I've come to terms with that fact about myself. Okay, so one up, one down. Oh, sorry, A, what's your question? What's your question, A? Our bond angles, they're all the same, and they're 90 degrees. Because going up and going like that, that's 90 degrees. And then the 4 around the middle, those are 90 degrees as well. Oh my gosh, I've got A. Do you know what? This is the problem. This is my problem. There are 2 A's in the chat. Okay. There is a capital A and there is a lowercase a. So, hi, lowercase a. Hello. Okay, these are all 90 degrees. Yeah. Yeah. Where's uppercase A? I mean, uppercase A has been here from the very first live stream, so I think they might take the OG. There we go. See, there we go. Okay, so again, our electron pairs want to be as far away from each other as possible. Okay, because electron pairs repel. But when we haven't got just bonding pairs, that's when it gets a bit more complicated because lone pairs, which are non-bonding pairs of electrons, they repel more than bonding pairs do. Okay, so all electron pairs repel, but bonding pair repulsion is less than the repulsion between a lone pair and a bonding pair, which is less than the repulsion between a lone pair and a lone pair. I know, A, how exciting. So, and I'll show you how to figure out how many bonding pairs and how many lone pairs coming up next. But first, let's see how our lone pairs actually affect our shape. No, A, this is A level, so you'll see this in year 12 when you join my A level chemistry class, okay? So if we've got 3 bonding pairs and 1 lone pair, the total is still 4 electron pairs, so our shape is still based on tetrahedral to start off with. So we can start there. Okay, lovely. Okay, so our shape is based off of tetrahedral, but because only 3 of these are bonding pairs and 1 is a lone pair, I'm going to change one of my bonding pairs to a lone pair. Now, I like to draw my lone pairs like this, okay? But some people, and I understand why, prefer to draw them like a little lobe. So like, ooh, like that. Okay, up to you. Now, if we had all knowledge is good knowledge. Oh, I like that. Oh, it depends what you do with it, I guess. So, if this was tetrahedral, what would the bond angle be? If this was tetrahedral, what would the bond angle be? Remind me. Lovely Keen, thank you. 109.5. But because lone pairs are going to repel the bonding pairs more than if it was just a bonding pair, that's going to reduce the bond angle. So think about the lone pair at the top, like squashing and pushing the other bonds closer to each other. And for every lone pair that we have, our bond angle is going to decrease by approximately 2.5 degrees. So rather than having a bond angle of 109.5, our bond angles are going to be 107. Absolutely. Oh, can't you be both? I think you should absolutely be a nerd, Aria. I think it's one of the best things you can be. That's what I tell myself anyway. Okay, 107 degrees. Nice. Okay. And that's because lone pairs, why did I start writing in capitals? I don't know, but I'll start it so I'll finish. Repel more. I do need a nerd hat. I absolutely do. I do. There's a t-shirt that I really want to make, and it's gonna say Miss Moles. So instead of Mr. Moles, I am Miss Moles. Okay. Next, we have got water, two bonding pairs and two lone pairs. Again, that's 4 electron pairs in total. So we're still based off of a tetrahedron. Okay, so we'll start with our central oxygen atom, one up, one down, one coming towards you, and one going back. But because only 2 of these are bonding pairs and the other 2 are lone pairs, I'm going to get rid of 2 of these. This is all exam boards. Any A level that you do, you will have to do shapes of molecules. Okay, this is year 12. Often this is drawn slightly simpler as just this, but both of these shapes are exactly the same. Just flipped and reversed and rotated. Now, again, because we're based off of 4 electron pairs, so we're based off of a tetrahedron, we would expect our bond angles to be 109.5, but our lone pairs are going to reduce those bond angles. How much is our bond angle going to be reduced by? How much? By 5, absolutely, lovely, because we've got 2 lone pairs, 2.5 per lone pair. So we're going to minus 5, and we end up with bond angles of 104.5. Absolutely. Oh no! I'm glad that I made the 10 out of 10 though, Aria. I mean, not just me, but chemistry in general. Great. Okay. So this is the basis, how we can draw our shapes and how we can determine the bond angles. But we need to know, based on just the formula, how do we know how many bonding pairs and how many lone pairs? Okay, now there are a couple of ways we can do this. I'm going to show you the dot and cross first, just so that you can see where all of this is coming from. Okay, so if we have NF3, I mean, we kind of just saw that, but let's do it anyway. Hi, Yashi. Hello, hello. If we've got NF3, then nitrogen is our central atom, and nitrogen is in group 5, so it would have 5 electrons on its outer shell. Okay? Fluorine is in group 7, So they need, they each need one more electron, which means that they're going to pair up with just one of these nitrogen electrons like this. Okay. Now, of course, fluorine also has its non-bonding electrons, its lone pairs, but to determine the shape, we don't care about fluorine's non-bonding electrons. We only care about the electrons around the central atom. Yes, this is like a dot and cross without having to draw all the circles, right? At GCSE, you get used to doing things, it looks like this, right? This is just like a much stripped back version. So based on our dot and cross diagram, we have got three bonding pairs, so three pairs of electrons that are involved in bonding. And we've got one lone pair, so one pair of electrons that's not involved in bonding. So exactly the same as we just saw, three bonding pairs, one lone pair. We get the shape that's based off of tetrahedral. Absolutely, just like ammonia with one lone pair. Remind me of the bond angle, please. What was the bond angle here? Oh. Anyone? Lovely A, 107 degrees. Lovely Sahar, lovely Chinwendu. And the shape name is called trigonal pyramidal, or sometimes it's just called pyramidal or pyramidal, depending on who you're talking to. I say pyramidal, okay? Because it's like a pyramid, right? No, A, there are lone pairs everywhere, okay? We're going to meet some more places where we see lone pairs, okay? Now, that's one way to do it. I'm now going to launch my new way. Yes, absolutely, Chinwendu, in mark schemes, if you call it tetrahedral, you'll still get the mark. Yes. Okay, now the other method, which is just like counting, so you don't need to draw the dot and cross, you can figure out how many bonding pairs and how many lone pairs there are. Am I not live on TikTok? I should be. Am I not live on TikTok? Oh no, that's not good. Help me. Someone help. I should be. Okay. So we would start by looking at how many electrons we have. Actually, no, we won't. Let me use my new method. Okay, so to figure out the shape of NF3 using a counting method, we can first just look at this small number here, the 3, and that 3 automatically tells you that there are 3 bonding pairs. Okay, now we need to figure out how many lone pairs there are. And the way that we can do that is we look at how many electrons are around nitrogen's outer shell. So that is 5. And then we subtract the number of bonding pairs multiplied by how many more electrons that atom needed. So fluorine is in group 7, so only needed one more electron. So just 3 times 1. And that gives us 2 electrons left over. And if there's 2 electrons left over, that means that we've got 1 lone pair. Any questions? This is exactly the same. So I've just used the same shape, just in a different example, just in a different method rather. So it's exactly the same, 3 bonding pairs, 1 lone pair. We've just worked it out in a different way. How do we get 1 lone pair? Let's label this working out. 5. Oh, hang on. Let me do it separately. 5 minus 3 times 1. The 5 came from the number of electrons on nitrogen's outer shell. So number of central atom outer shell electrons or valence electrons. Okay, the 3 comes from the number of bonds. And then the 1 comes from the number of electrons that each bonded atom needed. Okay, if we're dealing with fluorine, so any group 7 element or hydrogen, that number is always going to be 1. Okay. Yes, Chinwendu. So that's the way that I used to do it, but that doesn't work when oxygen is involved, which is why this is my new favorite method because it works all the time. Okay. Let's do another example. Let's do an example with oxygen so we can see how it works in that context. Okay. That means number, A. That means number. Yes. Hi, Gospel Singer Girl. Hi. Yes, this video will be on my channel after it's done. Absolutely. Okay, so let's do the next example. We've got, hi Hassan, lovely. So we've got SO2, so sulfur dioxide. Let's go straight to our counting method. Okay, from the 2, we automatically know that there are 2 bonding pairs. Okay. And because it's oxygen, we know that these bonding pairs are going to be double bonds. So 2 bonds. 2 bonding pairs. I'm going to say 2 bonds instead because they're not really pairs. Right? 2 bonds. Recovery me, hi. So they're meant to be half an hour, but I always go over because I get overexcited and I do them once a week. Okay, usually they're on a Friday. The time might change a little bit, but I always post on my social media what the latest time is. And if you subscribe to my newsletter, and you can get the link in the description for this video, then it will be in the newsletter, the time and the date for the live every week as well. Okay, so we have got 2 bonds because of the 2 oxygens. Now to figure out how many lone pairs, we'll take our sulfur. Okay, sulfur is in group 6, so 6 valence electrons. Then we subtract the number of bonds, which is 2, multiplied by the number of electrons that each oxygen needed. Oxygen is in group 6, so needed 2 more electrons. So instead of just 2 times 1, it's going to be 2 times 2. And so we end up with 2 electrons left over, and therefore 1 lone pair. Okay, so we can see we've got 2 bonds, so 2 bonding pairs, and then 1 lone pair. Okay, any questions there, please, please, please let me know. Otherwise, now we're going to go into what that shape is. Which bit, Waleed? Which part of getting the lone pairs? Maybe rewind for when I went just step by step just now. So because in total, we've got 3 electron pairs, our shape is going to be based off of 3 electron pairs. What's the base shape? Lovely, A. It's so satisfying, isn't it? Yeah, Aristoteles. Yes, if you prefer to do a dot and cross method, absolutely do that. Okay, if you prefer to draw it out, it will work just the same, but lots of people prefer not to draw it and just to do some maths. Sorry, which A? Capital letter, capital A. Maybe I'll just shout it. A and A. I don't know. Okay, 3 electron pairs, so based off of trigonal planar. So like this, like this, like this, and like this. But because only two of those are bonding pairs, one of them is a lone pair. So I'm going to get rid of it and turn that into a lone pair. How is it 3 electron pairs? There are 2 bonds, well, 3 electron regions. When they're double bonds, you're right, they're not pairs, but we kind of still consider them as pairs because double bonds will respond in the same way as single bonds when it comes to figuring out the shape. Okay? Now the question is, what's the bond angle? Why would you have one lone pair? Because we had 2 electrons left over when we did our 6 minus 2 times 2. Okay, Maya, redox is coming soon. 6 from sulfurs, valence electrons, 2 from the number of bonds, and then 2 from the number of electrons that oxygen needed, that each oxygen needed. You thought what was 4? What was 4? I agree with 117.5, absolutely. If this was just trigonal planar, it would have a bond angle of 120 degrees, but because we've got one lone pair, that's going to be decreased by 2.5, so we end up with 117.5 degrees. Okay. Ooh, okay. Any more questions there? We're going to do one more example. Before we look at a couple, maybe. Okay. Last one. I think we'll stick to half an hour today. So POCl3. Our central, actually, no, well, let's start off with how many bonds are we going to have? How many bonds to our phosphorus? How many bonds to our phosphorus? Not 5, not 3, not 5. Phosphorus, this is our central atom. How many other lovely 4, 3 chlorines and 1 oxygen. So we're going to have 4 bonds. Okay, again, I'm not saying bonding pairs, just because as soon as we see that oxygen there, we know that's going to be a double bond. Okay, but we'll worry about that later. Caden, 9.9 times out of 10, yes, the first element is the central atom. The only time really that you'll see it not be the central atom is with water. So H2O, where the oxygen is the central atom, even though it's last. But yeah, the rest of the time, the first one is the central one. Okay, so let's figure out how many lone pairs we have. Oh, okay. Actually, no, I'm going to ask you to talk me through it. How do we start? Oh, nice, Aria. How do we start? Hello, hello, hello. Lovely. Recovery me. Phosphorus is group. So phosphorus is valence electrons. Phosphorus is in group 5. So that's going to be our first number. Hi, is there another A? Is this a third A? Oh my, is there? No, same A. Okay, you scared me. Then we're going to subtract the bonds that are being made to the phosphorus. Okay, so, okay, still you. Now we've got 2 different elements here, so we need to consider them separately. The oxygen is in group 6, so that's going to be 2. So 1 times 2 for how many electrons the oxygen needs. And then the chlorine is in group 7, so only needs 1. Fantastic. So 3 times 1 for the chlorine. What do we end up with? Oops. Absolutely. We end up with 0, 5 minus 2 plus 3. So 5 minus 5 gives us 0 electrons left over. So there are no lone pairs. Absolutely. So if we've just got 4 bonds or 4 bonding pairs with no lone pairs, what shape do we have? Absolutely. Recovery me, tetrahedral, lovely A. So POCl3, so tetrahedral. And this was a past exam question, the shape of POCl3. The oxygen one, though, we know is going to be a double bond. So I'm going to draw one of these as a double bond. Technically, it doesn't really matter which one you choose because all 4 of these bonds are equivalent. They're all the same. So whether you chose to put the double bond up at the top or the side, it doesn't matter. It's easiest to put it up at the top because if you try and make one of these wedged bonds double, it gets a little bit confusing. How do we know it's a double bond? So we think about the group that the element is in, right? Oxygen is in group 6. Which means it has 6 electrons on its outer shell. So that means that each oxygen will need 2 more electrons to complete its outer shell, to fulfill its octet. So if it needs 2 more electrons, it's going to form a double bond. If it's only bonded to one thing, or 2 things separately, but here it's not. Okay? For group 7, so fluorine, chlorine, bromine, iodine, and also hydrogen, they all only need 1 more electron to fill their outer shell. So they only make single bonds. Okay? It does a nitrogen, right? When nitrogen bonds with itself, this is it makes it blah blah blah. What am I trying to say? This is a triple bond, yeah. And it's why nitrogen typically makes 3 bonds in total because it needs 3 more electrons. So if it's just bonded to itself, it'll make a triple bond. If it was bonded to 3 other things, then it's 3 single bonds. In the same way, if oxygen is bonded to itself, it's a double bond. But if oxygen is bonded to something else, then it's to 2 other things, then it's oh my gosh, to 2 other things, then it's 2 single bonds. Okay, 1 double bond or 2 single, 1 triple bond or 3 single. Okay. It's not necessarily that fluorine can allow other elements to break the octet rule, because of how it interacts with the electrons. And it's always it's always elements like sulfur, for example, where the D subshell is very close in energy, so it can kind of get involved in the bonding. And so it can actually hold more than 8 electrons. It could technically hold up to 18 in theory. Nitrogen bonded to one other thing, well, really it's just N2A would be the example. I don't know if is there another one? Cyanide, right? The cyanide ion, also triple bond. Okay. Oh, okay. Do you want to do one quick question before we go? One MCQ? I'll only stay and do this question if there is just so much enthusiasm. Like I need a ridiculous amount of enthusiasm. Otherwise, I'm just going to go eat my dinner. That's not enthusiastic enough. Okay. All right. Gospel Singer Girl is holding it down for the rest of you. There we go. Okay. Okay. So, which of these has a bond angle of 109.5? Actually, maybe we'll do more than one MCQ because I think this one might be quite straightforward, maybe in theory. This requires our understanding of bonding, right? And giant covalent structures. So if we think about diamond, in diamond, how many carbon atoms is each carbon bonded to? Oh, hey, you're ready to give me the answer already. Yeah, 4. So in diamond, each carbon is bonded to 4 others. Okay, and that's in a massive structure. So then each of these carbons is also bonded to 4 others as well. But if you were to just look around one carbon, then that bond angle around that central carbon would be 109.5 degrees. So the answer is A. That was easy. Okay, we're not going to stop there though. Let's figure out the bond angles in all of the other 3 so that we know that we've really got it. Okay, for graphite, how many carbon atoms is each other carbon bonded to? Wait, how many carbon atoms is each carbon atom bonded to? Yeah. Lovely, Caden. 3. Okay, in our, hexagon that would just continue on, but each carbon atom is bonded to 3 others. If we were just to look at one of our, and well, we know the shape as well for graphite, these are planar. Each carbon atom, 3 bonding pairs, no lone pairs, because that 4th electron, remember, is delocalized. So what's the shape around each carbon atom in graphite? If we were just to look at each one, what's the shape around each one? Ooh. Trigonal something. We can't just say trigonal. Lovely, trigonal planar. And what would the bond angles be? Lovely, 120 degrees. Wonderful. Well, 4, yes, indeed, A, lowercase a, yes, indeed. D, we can do super quickly because we saw that example so many times, and ammonia or NX3 should be one that you just spot immediately as what shape? We've seen it twice already this lesson, or this session, rather. NX3 always has what shape? Lovely, gospel singer girl. Pyramidal or trigonal pyramidal, depending on how you want to say it. Pyramidal, where we have our 3 bonding pairs and our 1 lone pair. For ammonia, again, or NX3, don't spend your time trying to figure out the shape for ammonia. This should be one. This, along with water and BF3 and CO2, those should be shapes that you just know off by heart because they come up so much. Okay, Aria, I will see you on Tuesday. Okay, have a nice weekend. NH2 minus, that's where we're going to need to think a little bit harder. So we can use our approach, okay? Nitrogen is in what group? Hello? Hello? Oh, no, sorry. Tuesday is when we have our MES full lesson. So in the course, there are 1 hour lessons for year 12 twice a week, hour and a half lessons for year 13 twice a week as well. You get a workbook, you get homework, you get video solutions. So that's as part of the Myad Space course. So if you're interested, I want to say the link is in the description. Okay, maybe it's not. But if you go to myadspace.co.uk, then you can have a look at that too. Okay, so thank you. Group 5 for nitrogen. Then we're going to subtract 2 lots. Yes, I'm sorry. Yes, A, absolutely. Same for GCSE. Yes. 2 times 1 for the hydrogen. My ed space. I'm going to type it in the chat. myedspace.co.uk. It's not, it's free. It's not free. It's not free. Okay, so minus 2 times 1 for the hydrogens. Okay, but then we need to add one more electron because of this negative charge. Okay, oh, I2 stem is, oh, I see. Sorry, okay. I thought you meant my space is free. I was like, wow, that would be, I mean, this is free, this live stream. So we end up with, what do we have? 5 minus 2 plus 1, 4 electrons left over, so 2 lone pairs. So we have 2 bonding pairs and 2 lone pairs. You're absolutely right, Chinwendu. It will be bent just like water. Bond angles? Oh, I didn't ask for the NH3 bond angle. I'm going to ask you for both. Not 107.5. We've got 2 bonding pairs. Sorry, 2 lone pairs. So our bond angle is going to decrease by, I am in London, yeah. 104.5, lovely. And just to finish off, what's the bond angle for NH3? Ooh, 107, absolutely. So 109.5 minus 2.5. Not, remember, it's minus 2.5 per lone pair. So it won't be 107.5, it will be 107. 109.5 minus 2.5. Okay. Okay. Yay. Wow. These are the future mods. What do you mean, the future mods? Oh, maybe, who knows? Who knows? I think if you're talking about what I think you're talking about, maybe. We did a lot. We did a whole bunch in 45 minutes. So I'm really impressed. Who's gonna be mods, eh? Oh, for the lives. To be determined, TBD. Okay. For now, really, really, really well done. Please, before you go, please like the stream. Thank you so much. Thank you for joining me this evening. And next week, what did we say next week? Can you remind me? One of my year 13s. What did I say for next week? I want to say, I think I said rate. Did I say rate equation? Gospel Singer Girl in the description for this YouTube video. You'll see it says sign up to my newsletter for free resources every week. Okay, so click down there. Okay, rate equation next week. Again, look out for in the newsletter for the date and time. Also, please make sure that you follow me on TikTok and or Instagram, and then I always post with reminders for the times as well. Okay, great. Yay. Bye. Yes, well, the week after, I'll make sure to do a year 12 topic. So we'll focus on, I think, redox after next week. Okay, so rate equation next week, redox the following week. Okay, all right. Bye. Link, the description will have the link for the newsletter. Okay, description has the link for the newsletter. Okay, bye.